Okay. Good morning, everyone, or good afternoon to Philip, who is in Europe. And today, what we're going to do is because we released some new data set recently, and which can be used for this particular collaboration activity. So today, my PhD student Hamad is going to give a talk and talk about the paper together with that release of the data, where you're going to find the data, some of the preliminary analysis done in that paper. So without further ado, and Hamad, whenever you're ready, you can share
Sure.
screen.
Excuse me, Professor, could you see my screen?
Yeah, can you make it a full screen? Right now it's in file format. This is a presentation format.
Yeah. I'm sorry.
Can you just, yeah.
I'm sorry, just a moment. Is it better now?
It's still in that kind of presentation mode. So I think there's something you can display setting. You needed to, there's something swap, yeah, the view and the slideshow. Yeah, good.
Okay, sorry about. Hi everyone, my name is Ahmed. I'm PhD student in Dr. Yu Ding's team in Georgia Tech. Today I will go through a paper recently published by Effie, our previous teammate in Texas A&M. And this paper discusses how the leading edge protection may affect the energy production. So uh, the leading edge protection is when over the time some damages occur to the blades, like erosion. The treatment is to use tapes or painting the blades or etc. Called leading edge protection. And the challenge is to measure after making this technical change, how much the power production, how much the power production gonna get changed. The issue here is like if we just take the power after the change and then the before the change and subtract it, it might be affected because of the weather change. Like in this data set, which the article used, 5 turbines are very close to the sea, and there is high chance of having drastic weather change over the time. And so here the idea is how can we decompose the change in energy to the change because of the weather and because of the turbine's intrinsic change. In this farm, all 5 turbines are from same make and model and from 2 megawatt class, and the whole farm is producing like 10 megawatt. The data is for 7 years from January 2013 until October 2020. The authors divided this data to 4 periods, all of them more or less 1 year. And the first period is just starting 1 year before the first LEP application, which is done on 5 turbines. So first period is from June 2015 to May 2016. Then the second period is from September 16 to September 2017. And then the second technical change is blade repainting, but it's done on only turbine one. And finally, the second LEP repair is from August 2019 to September. And in today's work, the tables I will show and we'll go through them are focused on periods 3 and 4. So two, they are looking to the effect of second LEP repair. To access the data, you can just go to Dr. Yuding's personal website, and then the Data Science for Wind Energy book is available there. You can download the book or the data sets. It's free to use now. And the data sets, you just click on them, and then the next page has all data sets this book use. If you just scroll it down under the extension data sets, the first one is energy decomposition data set. There, you can access to the data set, the codes for this paper, the production report, and paper itself. When you click on the data, the Zenodo website can pop up, and there you can download the data in a zip file. For each turbine, is partitioned to 3 parts for easy handling to the softwares. So there is 5 turbines for each one 3 parts, altogether 15 CSV files in this zip. And also the code is uploaded to the Zenodo, so you can easily download the whole code for producing all tables in the paper in a zip file. But after like extraction of the data and codes, in case you wanted to reproduce this work, please remember to change the path to the folders, to your local path. And then, for example, the first table we're gonna see is table 5. Reproduction report helps us to see like which one of the scripts need to be run first in advance to the main script of table 5. Here, the required data for table 5 is imputed R data and repgp5. Those are actually the script all for data imputation and synchronization, and O5 GP power curve model. So for reproduction, those scripts need to be run first. Next, I will discuss how the authors did the data pre-processing and imputation. As we see, there's 3 parts for each turbines. First, they merge the 3 parts together, and then as they focused on periods 3 and 4, they just take 1 year of data from period 3 from 2018's 9th months to 2019, and then another 1 year of data from 2019's 10th months to 2020's 10th months. So they are for both periods before and after technical change. There is 1 year of the data. And then they filter the data to make sure there is no data aroused with turbulence intensity smaller than 1 or turbulence intensity is higher than 1 or temperature higher than 40. It's not rare to see high temperatures, but this location is very cold, so that's why they filter the temperature over 40. Then they removed the missing values and matched the timestamps for all 4 turbines. And finally, they matched the lengths of the data for periods before and after the technical change. The reason of this part is because they will do energy decomposition, and energy is like highly related to the time. So if the length of data is higher for one period, it's probably gonna have higher energy production. That's why they match it. Then the next step is data imputation for actually replacing the missing or not valid values of power. they do a two-step imputation. First step is creating some temp Gaussian process models using TempGP. But they first filter to the data to between cut-in and cut-out speed from 4 to 25. And then they remove the raws with negative or zero power in that segment. And then they fit 8 temp GP models because this study just uses turbines 1 to 4, and each one of them has 2 periods. The model is taking only speed as input, and temp GP is a Gaussian process model which handles temporal autocorrelation. In previous studies, we've seen that temp GP has at least 20% better accuracy compared to other machine learning approaches. So in this script, it stores 8 Gaussian process models and then uses them for imputation for the speed from cut-in to rated. So from cut-in to rated from 4 to 14 meters per second, I just imputes the Y with this model. And for the speed lower than cut-in or higher than cut-out, it just imputes with 0. For between the rated and cut-out speed, it uses the maximum observed power for imputation. Then the next slide is about the methodology overview. So assuming that there is 2 periods of data and one before technical change, one after that, you can call it as D1 and D2. Also X1 and Y1 is for D1, and input and output of period 2 is with X2, Y2. The F model, the F power function, is also associated with each period. And as F gonna be modeled with Gaussian process model, then the noise is assumed to be a Gaussian noise with 0 mean and sigma square. So the aim is to decompose the changing energy to 2 parts of changing weather, change due to weather and change due to turbine. First, author discussed delta E of weather, and to get that, to estimate delta E weather effect, it assumes there is an ideal turbine which does not have intrinsic changes, and the power function is constant. So to just approximate the change because of 2 weather conditions, someone may apply this power function to the second period and apply it for the first period and just subtract it. However, the challenge is like in practice, there is not such an ideal turbine. So, but in this case study, we have like 2 power functions. So author approximates the delta E of weather by uh, doing the same thing in both these power functions and then averaging on them. So once it applies power function 1 on weather condition 2 and subtract it from weather condition 1, and then same thing for power function 2 and then the average. Then to approximate the turbine effect, we have almost the same steps. So author assumes that there is such an ideal weather condition which there is no drastic weather changes. Then the turbine effect can be approximated by applying power function 2 and then minus power function 1 on the ideal weather condition. But in practice, the weather condition cannot be guaranteed to be separate from the drastic changes. That's why it does this process on both weather conditions and then takes the average. So this was the methodology, but actually the ratio is the number, the statistic that we're gonna use in the in practice. So for both these delta energies, it just divides them by average total energy, and then I will get the ratio. So average total energy is just the observed Y summed over a period before technical change and period after technical change and average. So one thing to mention is like what we discussed now is just applying the power function on data one and data two, such that data one is period before change and period two is after change. But this can also be done on same period for different turbines, which we'll see in the next few slides. But first, the code for doing this temp GP models and then getting the statistics is O5 GP power curve model. So as I said, there's like this tables are studying 4 turbines from 1 to 4 and 2 periods of before and after the second LDP change. So the 8 GPs are needed for 8F functions. And the output is power, but input is not only speed, like the pre-processing step, but now we have more features like temperature, wind direction, standard deviation of direction, and turbulence intensity. In the data set, there is more features like pitch angle and rotor speed, but the reason that author goes with this subset is because they performed a tenfold cross-validation and this subset achieved a loss error. Then the energy decomposition is actually approach 2 in this paper. There is another approach which is discussed in another paper with more details, but here it's just reviewed. And this is called power decomposition. I may go through the power decomposition in next month's meeting or sometime in the future, but it's really easy to use. So in DSWE package in R, the function is compare P curve, and there is also a small example shows how to use it. So it's just creating a list of the data and then specifying the X and Y columns and just feeding them to the function, and function gonna give the relative statistics. In case that you want to use this function, you can just take a look to the reproduction codes or the GitHub page of DSWE package. Next, we can see the table 5 results. Here, the first 4 rows are for approach to energy decomposition, and last row is for power decomposition, which I really did not discuss the details. But for energy decomposition, we can see how each one of the statistics is calculated. Observed delta E is actually just taking the sum of actual imputed power on first period and then taking the sum of actual imputed power on second period, take the subtraction and divide it by the average. That way we will see the total delta energy for each turbine. So for each turbine here, the before period is actually period 3 before second LDP change, and period 4 is after second LDP change. So for second row, it's delta E hat. It's not observed data, but it's estimated. So the only change to delta E observed is not using actual power, but using predicted power. The power predicted from the temp GP models we already developed. And then the next row is delta E of weather. So delta E of weather, as we saw, is just applying each one of the power functions to 2 weather conditions and then making subtraction on weather conditions and then averaging. And last row is just on each weather condition, applying 2 power functions and subtracting, and then average on both weather conditions. One thing we can observe here is consistency over the numbers came from delta E of turbine with approach 1's power difference, because good thing about approach 2 is that it can numerically estimate both the delta E uh, because of weather and also the turbine effect. But approach 1 only can estimate the uh, turbine effect. So in comparison of fourth and fifth law, you see a consistency in the results. Next, the paper discussed T2P and P2T. Actually, what we have done so far is P2T. So we computed the delta energy and on two periods for each turbine, on periods 3 and 4 for all four turbines. In case that we compare the change of the power over the turbines and over the time, we can just take the subtraction of delta E T2 minus delta E T1, and then we'll get the delta E P2T. But another approach is the reverse side. So first, someone may take the period one's data for both turbines and treat the turbine one's data as D1 and turbine two's data as D2. And then by making a subtraction and the same period for two turbines, it will get delta EP1. And similarly, it can get the delta energy for period 2. And then if do the subtraction for two periods, the statistic will be delta E T2P. Actually, we expect these two delta E's to have at least close values. In this table, the author actually goes through the T2P approach. So it takes each pair of turbines from T1, T2 until T3, T4, and it computes uh, the delta E for period 3 first. So for period 3, as I said, it's like just taking the first turbine in the pair as data 1 and second turbine in the pair as data 2. And then the delta E hat of turbine will become the delta E for P3. And then it can be computed for all pairs, and same thing can happen for P4. And then subtraction of P4 minus P3 will become the T2P delta E. For P2T, we already had the table for table 5, which we discussed in a few slides ago. It's just making so in that table, the delta E hat of turbine was calculated for each turbine. In case that we just take the pairs of turbines and make subtraction, we get the results for P2T. For example, for the second row, turbine 1 and turbine 3, it's enough just to take the turbine 3's delta E and then subtract turbine 1 from that. It will become minus 2.30, the number in the second row of this table. One interesting observation is that the numbers coming from T2P and P2T have consistency, which we expect. And then we really did not go through the approach 1, but also the numbers coming from approach 1 have consistency with approach 2. Approach 1 is, as we see with the function compare P curve in R. So to just summarize what we discussed, new data is available. Please feel free to download it and try your own methods on that data. We would be interested to hear how the results are same or different from the results shown in this paper. Then we saw that energy decomposition can quantify both turbine and weather effect. And power decomposition method, approach 1, can only quantify the turbine effect, but there is also consistent with energy decomposition method. And we also showed the P2T and T2P, which is comparing the change in power production of two turbines over two periods. That's all for today. Thank you for your attention.
Okay, thank you, Hamad. I just want to add a comment and note the later part of the so-called P2T and T2P analysis. The purpose is really do a sanity check, right? Avoid any kind of inherent or numerical problems. If you use the same method to take a different route, either you start from turbine performance and then to do the period comparison, or you start with the period performance and then do the turbine difference comparison. These two results supposed to arrive more or less the same result, right? If it doesn't, it give you a kind of warning to say there's something numerically probably is inconsistent in the procedure. So thankfully, in this sanity check, the method at least passed the sanity check. The approach one, approach two, they are very different approach, and that give provide some degree of cross validation, if you will, because if the same data pass through two different kind of numerical method, it end up with very comparable. They cannot be exactly the same because the data manipulation is different. In the end, they show the consistent result. That give you some additional confidence. That result probably didn't happen by chance. It's not really kind of random error type of things. Okay. Any questions for Ahmad and from the audience or discussion point?
I've got one question, which is not directly related to the topic being discussed, but you mentioned using Gaussian processes for power curves, and you found them to be better than other models. That's not my experience. I found them quite hard to use and get good results from. I'd be interested to. I don't know if there's a paper you can share, or I'd be interested to hear your experience of using Gaussian processes for power curves.
Go ahead.
Yeah, actually, there is a paper that Abhinav Prakash authored, and he showed that over a set of trials from deep neural networks or from the support vector machines, XGBoost, random forest, I think, over a different set of the methods, the temp GP is doing a better job with a margin of 20%, but at least 20% actually. But the drawback of that model was the speed. It was super slow, like running on one set of wind turbine data would take more than 20 hours for 1 year. Yeah, but recently we developed a speed up version, which is Vecchia. So in the same package, the method now is existing. So you can just use the temp GP object. It's automatically set to the Vecchia version. It's now faster and it almost has the same accuracy. In case that you want to try that on some data and see how it works compared to your data, it's really easy to implement. Or in case if you had issues, you can share the data. I can give it a try. That's all on my side, Professor Dink.
Yeah. Okay.
So Philip, it's probably easy to try the package directly. We can share the paper as well. One of the reason that particular version of Gaussian process is because we handled one of the issue of the autocorrelation of the data, because you collect the data, they are time series sequential data, and they are 10 minutes apart. And with that kind of time resolution, you still have this kind of physical momentum of air movement, all these things. So the noise are correlated, the X are correlated, the Y, the power also correlated. And their research indicate, that kind of correlation will inadvertently affect how you select your final model. And if you get rid of that kind of effect, because if you only try to recover the power curve, that autocorrelation is an artifact. That shouldn't be part of the power curve. Okay? For a
Yeah.
certain kind of period, the power curve should be more or less static. In the longer term, like couple of years, the power curve shifted on itself. But for a shorter period of time, that power curve should be more or less static. So if you do something of that nature, actually it helps you with the accuracy. And that's why Ahmad mentioned in some of the early testing we did, this one comes more advantages. Last year on the same platform, we actually did a power curve study. It's a competition, right? So the TimeGP is also one method being used. It's not really the best method. There's some other method. They are getting very close with each other. So numerically, it's not really very differentiable, right? Within like 2.5% difference in the final result. But it's one of the best method in the final run. And Sarah and I wrote actually a conference paper summarize that outcome. And in the conference, it's one Europe conference, I believe, I can send you that conference paper as well. There's some summary of those analysis. So I can send you Ahmad can send you the software package link and the paper and also the WIN conference paper.
Yeah. Yeah, that'd be great just to have a look.
Sure.
I'm
Sarah
not sure
can,
how quickly I'll be able to get around to having another look at that, but it'd be very interesting.
Take your time. Yeah, he mentioned, Ahmad mentioned about the speed up. We recently complete that speed up. So previously you need quite a number of hours to apply the Gaussian process on a full year of data. But right now it's just a couple of minutes. And it doesn't really sacrifice much of your accuracy, the model accuracy.
Okay. Yeah.
Now, one of the purpose of this particular talk is really I want to bring to the attention because from the early discussion, we come to realize the initial set of data being shared, there's a certain kind of limitations because there's only 2 turbines and there's, before change period is multiple months, but after the change period is only multiple weeks. And so here, Wind Energy Institute of Canada allows us to share this set of data. It's multiple years. And generally, after certain change, there's 1 year, very close to 1 year data before the change and then 1 year after the change. Okay. So that probably will provide additional resource. And right now, the data is open access. And for folks interested in trying this new set of data. And but in order to root the data release in a context, right? This paper is really trying to study the LEP impact at a different kind of period. And initially the LEP application, and then there's repainting, there's repair, and how much each time we see at least in the original study, see the power performance changes. It's not always positive. Actually, in the initial LEP application, after the application, we see roughly on average a 0.5% decrease of the turbine performance. That surprised Wind Energy Institute of Canada initially. But afterwards, they sort of agreed to the finding. Yeah. Any other questions? And I think Sarah also.
She was just sending a link to the paper.
Right, that's the paper.
The results on the Relight platform. Yeah.
Yeah, I just had one question. I was wondering for the Gaussian process power curve model, what were the features that were used in the model? I may have missed it.
Okay. Let me just share that part again. So it was wind speed, ambient temperature, direction, standard deviation of wind direction, and turbulence intensity.
Okay. Yep. Clearly, I just missed it. Thank you.
But in case that you want to try another subset, I believe the data set has some other features like rotor speed, like pitch angle.
So Erica, on this particular part, what we generally advise is you of course can choose whatever you need to as an input. So the function itself actually is pretty accommodating, right? Generally speaking, there's two things we typically do. We usually do a kind of subset selection to see which subset of variables give you the best model with the fewest the input number, right? So this is like avoid so-called overfitting. And sometimes you only have like a very small increase, but you need to use the two additional variables. We would rather not to do that. Another thing is that there are certain kind of variables we exclude a priori, even before we do the data-driven test. So for example, the rotor speed in this particular case, because in this particular study, well, not only in this study, in many of other studies as well, the rotor speed is so strongly correlated with the power. If you use the rotor speed, it's almost like you can tell the power very, very accurately, and which is not really external variable. It's not really the environmental variable, right? So we exclude that rotor speed ahead of time without it. Otherwise, once this is really elephant in the room, once you include the rotor speed, you don't need anything else to predict the power, right?
Right. Yeah. And so those variables are coming from other turbines, like from reference turbines?
No, from
Or
itself,
from the
turbine
okay.
itself. So in this case, the wind speed is measured in the wake. So we just treat as in the wake, and even there's a caveat, right? Because the wind speed is measured in the wake. Once you repair or apply the LEP, it changes the flow condition in the wake. So the wake measurement, the nacelle transfer function will be somewhat different, but nobody really know how different it's going to be. And because they didn't really redo a calibration. This is the data go back like 6 years ago. They only have the data, they don't have anything else. So we just pretend nothing happened and use the data as is to do the analysis. So that's one of the caveat. If there's any better method to say, I can help you to, you also have the location of the 4 turbines. If you said I can use some of the relationship to say to get the wind speed more accurately, that'd be great. We didn't do that. Yeah.
Sure. Okay. Yeah, and then it's nice to see the standard deviation of wind direction being used, at least for wind farm control applications I look at. We find that's a really important variable, maybe even more so than turbulence intensity. But yeah, just a comment that's been useful for our research too.
Yeah, it's a good point. I'm presumably highly correlated to turbulence intensity or wind speed standard deviation, but nonetheless different, and can probably provide different information, as a lot of the performance would be due to sort of mini yaw misalignments, if you like sub 10-minute yaw misalignments. Interesting. I've got one sort of methodology sort of question. So when we do side-by-side tests, the way we do it is more, we filter the data of, so you have 2 turbines, we filter the data for samples when they're both in sort of normal operation or full performance, and they're both, for example, in a shared wake-free sector or something. And then we remove all the samples that don't meet that on both turbines and look at kind of the power ratio sample by sample, and then the distribution of that power ratio. Whereas you've gone about it quite a different approach, where you impute the data for the samples where presumably it's not meeting those conditions or it's missing, and then looking at the total, just taking the total power during a period and looking at the difference between those two turbines. So it's sort of coming at this from a different angle. I don't know if you've investigated that in different ways, or you've always sort of gone by this method, or whether you've considered both and you found this method to be better.
Yeah, that's a good question, right? The imputation is not exactly try to get rid of the wake effect of this kind of things. It's more kind of denoising, right? If you look at the table, Haman showed the imputed result and versus the raw result, they are to the second decimal point, there are not really that much a difference. I suppose it's probably because the data points are quite many. In this particular, and also the data quality is pretty good, to start with. Right, if you look at the delta observed, this is directly from the raw data versus the delta E with a hat. That hat is using the predicted value. I'm sorry, the delta observed is already imputed. So the imputation is really there's some kind of mistakes, some of the irregularity being used. So that difference. Now, one of the
Sorry, what are you imputing for? Like, because imputing is filling in missing data samples. So is that
right.
data samples that were entirely missing, or is this imputing for like downtime, for example?
They're both, right? There's a
Yeah.
missing data, there's a downtime, there's some very irregularity of the data. The data obviously doesn't really make much sense to those being imputed. Not necessarily for the wake effect. Now, one of the reasons we didn't really go through the route from just use the valid sector for comparison. It's probably because it influenced in the early years when I was doing this type of research, I was working with a few other industry partners. And they said that the value sector roughly is about 1/3 of the, if you only take the value sector, is only about 1/3 of the entire operation, right? If you take a whole year data, that's about 30% of the data you're going to use. So, which really means if you take the result, it means you can do the side-by-side comparison for about 1/3 of that time. What's the difference between the turbine? And the question is, will this 1/3 difference extrapolate to the rest of the 2/3 of the time when the two turbine operating?
Yeah.
Right. And to actual owner operator, it said, I really want to know the difference all the time.
Yeah.
And that's why at that time we thought, however, the model is imperfect and it's probably should just take all the information to do somewhat average, right?
Yes, your uncertainty and noise will be greater in the times when it's weight. I agree. Well, that 1/3, 2/3 thing you say is very site dependent, right? So you have some turbine pairs on a site where it's much higher than that, but of course, in a large offshore farm or something, then you've got the turbines in the middle. It's basically 0% of the time, right? They're always in some kind of wake. So there is that benefit. I mean, we've tried to do performance comparisons specifically in wakes conditions, and the uncertainty increases a lot when you increase include those conditions. So there's a challenge that comes with it, but I take your point that quite often we need to know that, or we need to consider those conditions to have enough data. Yeah.
Right. Yeah, I think that's still kind of ongoing debate. Is one part of the complexity arrived from this whole thing, right? And the inaccuracy of the wind speed measurement. But I do see the owner operators point on that, right? Because for them, for example, someone tried to sell them a new technology and said, I can increase your the wind turbine production efficiency by 2%. And that 2% is supposed to be applied to the whole year, right? Whether or not you are in wake or not, it's average 2%. And rather than to say I only increase that 2% for in the wake, but the 0.5, I mean 2% wake free and 0.5 in the wake type of things. So fundamentally, by the end of their bottom line is they don't really care it's in wake or out wake. Just tell me how much in the whole year the increase is going to be.
And it should, like, operating in the wake is probably unlikely to affect those performance upgrades. You know, they're not in general, I don't think, specific to wake or non-wake. I guess they might work worse in like higher turbulence, for example. And that's maybe part of the study. And what we've done, some clients is, you know, they've chosen in advance to put the upgrade on specific turbines, and we've informed them which turbines to put it on, so that we can do an analysis, and, you know, then you can choose basically wake-free turbines on the prevailing wind side of the site or something. So if you have that luxury of choosing before you do the side-by-side test, then it's good. But if it's something out of your control, like a performance defect or something, and it happens on a turbine inside the middle of the site, then yeah, it's a more difficult situation. Yeah.
Like in this particular case, there's not really that much opportunity to do side-by-side control analysis, because the 5 turbines, there's no other turbine being paired. You know, when they get the data, it was not really in their mind. So because this has already been done, and I think for the first time when they apply the LEP, there's a few different kind of LEP options to apply. Because the paper published a couple of years back, I don't fully remember whether or not they're all the same application being applied for 5 different turbines, or there's you know, different LEP choices being tried.
But in this case, you were comparing 2 turbines, right? Because the table had turbine 1, turbine 2.
That is only for, yeah. So we do, you know, the initial analysis is really compared for 2 periods, you know, for the same turbine before and after they do this action, you know, whether or not they have a positive or negative effect on the result. Afterwards, we try to do even turbine-wise comparison, and one of the reason is also you know, the request was raised by the engineers at the Wind Energy Institute of Canada, because they want to see, you know, whether or not how the turbine compare each other, also do the so-called sanity check, right? If you go this route, compare, and that route, compare, eventually the result should be comparable. And so Archa, you have a question. You said that, do you have data on different scenarios? What do you mean? Can you explain yourself a little bit more?
Hello.
Go ahead.
Yeah, thank you. I mean the data of different scenario of turbine behavior for detecting the faults.
Force, like the bending moment.
Faults.
Yes, faults.
Force, the failure, this kind of things.
Failure, yeah.
Yeah, no, we have a set of data, but they don't really allow us to release that data. The failure data is difficult to obtain. There's an open set of data from EDP. They have some of the failure data. There's an EDP open data.
Can you write this for me, please?
EDP, Portuguese.
EDP, okay.
Right. So one of the places you can go is to this IEA Task 43 website. So several of us are working for this IEA Wind Task 43, and as a part of that effort, we collect the open data to put on one page, and that one page give you one stop. We don't own the data, right? But give you a kind of pointer to where to find those kind of data. Now the only places I come across, because I lead that effort to collect the open data, I come across there's a fault failure data is really from the EDP open data. There's a lot of data out there, but most of them don't have failure data.
Yes, I didn't find the failure data for a different scenario, and it was difficult for me.
Right. So try the EDP open data, and that's the one has the failure data.
Okay, thank you.
Any other questions, comments? Okay, I suppose we probably conclude today's presentation. Thank you very much again for Hamad for your talk, and we are reconvene 1 month after. You know, Hamad probably can continue finish the rest of the paper, and there's some other study done in the paper, and also could possibly explain the so-called approach 1 a little bit as well. Okay.
Thank you so much.
Yeah, thank you.
Thank you.